My parents are probably like, what?
Megan. Who do you need to? Your room, okay? You go to your room. Okay, good morning, everyone. So, as usual, we're going to answer the quiz or problem solving that we have. So, these are the questions that came out. The only one that changed there is the wavelength or the length of the thing. So, the wavelength of the green light from a traffic signal is centered at 0.055 meters. So, calculate the frequency. Okay, so this is the a very straightforward thing. So as you could see, speed of light is equals to, I have to make this into a slideshow. Megan, can you go inside the room? Come. So we have the wavelength times the frequency. So the one that's being asked now is how much is the frequency. So if you're going to put it on one side, you just divide both sides by the wavelength. So the frequency is just equals to the speed of light times wavelength. So if you're going to do this, so this is 3.00 times 10 to the 8 meters per second divided by whatever is the given value that you have there. Okay. So that is equals to there's 1.5 that's missing. So we will put it in terms of 5.41 times 10 to the, or the way I asked you to do exponent positive 10. If you're going to write it based on the format that is in your Blackboard. Okay. And I graded it manually. So if you don't get it correct way, you get something out of the thing. So let's try to recall what we have done last meeting. So as I've told you, we started with the dual nature of light and then the dual nature of matter. So de Broglie is the one who proposed the dual nature of matter. Okay, so that means matter is not always only particulate; it also has its wave property. Okay, I found out that quantum applies to all matter, not just radiation and light. In other words, for all of reality. And then we said that Heisenberg, okay, came up with the uncertainty principle. There will always be uncertainty either about the place or the speed of a particle. So we cannot measure both at the same time. Okay. And in the Copenhagen interpretation, you have their Heisenberg, Born, and Bohr. So they come up with this statement. Apparently, this uncertainty is real and fundamental. So particle has no specific position until we measure it. Before the measurement, it exists in a kind of probabilistic state. So we could say the dual nature of matter that we have is just like this one. Okay, so this is some sort of the wave-like property of, let's say, if it's if you've seen a ghost, if ever they exist. Okay, so what you have there is a wave-like property. But as I've told you, it has something to do with Schrodinger. Okay, and the evolution that we have there. So from the Schrodinger equation, wherein he looked at the probability where you're going to find the electron, the so-called wave function. Okay, and together with Werner Heisenberg, the uncertainty principle, they tried to come up with a new model that best describes the atom. Okay, so if we're going to look at the evolution of the atom as we go on from the chapter 2, we started with Dalton. Okay, wherein it says atoms is the fundamental particle of all matter. And then you have the Thomson model, the plum pudding model. okay, where he discovered the electron. And then you have Rutherford, which formulated the nuclear model, okay? And then you have the Bohr model that we have discussed last week. This is the planetary model, and this is the Schrodinger model, or we could say it's a QMM model. So in the model put forth by the quantum mechanical model, which is spearheaded by Schrodinger, okay, the electrons that we have there is something to do more of probability, okay, than certainty. So there's Schrodinger, Heisenberg, okay, what they said is the electron is most likely found in a region, not in a specific area. Okay, so it's more on the model that they have is on the probability on where to find their what we call electron. And usually they said this probability of things that they have, okay, they come up with a term for that. Still adopting Heisenberg uh, thing, or we could say in terms of the this one. So what do we call this thing here? You call it an orbit, right? So what the quantum mechanical model adopts, instead of calling them an orbit, they derive the term called the orbital. Okay, so orbital is the region that you can probably find the electron. And they said, using quantum mechanics, each electron is described by 4 quantum numbers. So you have here the principal quantum number, the angular momentum quantum number, the magnetic quantum number, and the spin quantum number. Okay, so what does it mean? You have 3 of the 4 quantum numbers you can find, okay, the wave function of the particular electron. So as it says here, the first 3 quantum numbers define the wave function for a particular electron. And the fourth one just refers to the magnetic property of the electron. Okay, so you may ask yourself, what is this wave function that is put here? So that wave function that we have there, before we go there, this is just, okay, what an orbital is. So a wave function for the electron in an atom is called the atomic orbital. So we could say the orbital, that's where you can locate your electron. And an orbital, each orbital is described by 3 quantum numbers. So if you have the orbital, is describes a region of space with a definite shape where there is a high probability of finding the electron. So what we're going to do now is we study the quantum numbers and then look at the atomic orbitals. Okay? Now, if we want to summarize the quantum number that we have, these are the things. So this is the first quantum number, the second, the third, and the fourth quantum number. And if you're going to look at this, the name that they have, they may differ with the one that we have in this slide. So we call it the principal, the orbital quantum number, which we could say the azimuthal later on, and then the magnetic quantum number, and then you have the spin quantum number. And if we're going to describe them, okay, in terms of S, so this is something to do with the size, the shape, the spatial orientation, and this is something to do with the spin. Okay, but we're going to discuss them, each of them, okay, and what the role that they have. So if you're going to look at this, 1, 2, 3, it describes an orbital. And the fourth one describes the spin quantum number that you have here. Okay, so let's go with the first one, the principal quantum number. So if we're going to look at the principal quantum number, we designate it as small letter n. Okay, so the principal quantum number that we have here, it's the one on which the energy of an electron in an atom primarily depends. Or we could say the principal quantum number governs the size of the orbital. So the smaller the value of n, the lower the energy and the smaller is the orbital. And the possible value of your principal quantum number, they're always positive. So when we have orbitals with the same value for n, okay, we say they are in the same shell. So n, we could say that's your shell. Okay, so principal quantum number. So in some books, you can designate them by uppercase letter, but here we're going to use them as number. Okay, so exclusively, the n will be equals to positive numbers that we have here. Okay, so that's the first quantum number. Maybe right now you're still abstract, so what? Okay, but when we going to talk about it and then combine what they are, I hope that you be able to have an understanding of what I'm talking about. So the second quantum number is the angular momentum quantum number, and it is designated by small letter L. So if n is equals to the size, L has something to do with the shape. Okay, so this quantum number distinguishes orbital of a given n having different shapes. Okay, so it can have values from 0, 1, 2, 3 to a maximum of n minus 1. So what does it mean? Its smallest value would be 0 to n minus 1. Why do you think the smallest value is equals to 0? What's the smallest value of n? Anyone? What's the smallest value of n?
1.
1. So if you have 1 minus 1, that is equals to what?
0.
0. That's the explanation why the lowest value of L is a 0. Because L depends on n. Okay. Now, what does it tells us? So when you have n equals to 1, so the only possible value of L is what?
0.
0. So that means when n is equals to 1, you only have one shape of the orbital stir. Now, when n is equals to 2, what's the possible shape? You have a 0 and a 1. Okay. So what does it tells us? The L depends on the n. Now each
Yeah, I
of
just have a
these
quick
0,
question.
huh?
If n equals 2, how can L equal 0?
No, look. It can have values from 0 to n minus 1.
Oh, okay. Thank you.
Okay? Because this what we call quantum number, it refers to the shape of the orbital that you have. Okay, you will learn about it as we go on, but I'm just telling you, okay, how do we get the values of L? So we could say here, the L depends on the N.
Gotcha.
Okay, so if N
Okay.
is equals to 1, your L is only equals to 0. There's nothing other number than 0. When N is equals to 2, it can have a 0 to 1 because it is from 0 to N minus 1. So 2 minus 1 is equals to what? 1,
1.
right? So that means it can have a 0, it can have a 1. But look at how I designate them. I put an N here, I put an L here, and then I put a 2, and then I put a 0 here, and then I put what? A 0 here, and then a 1. Okay? Now, orbitals with the same values for N and L are said to be in the same shell and subshell. So if this is the shell, this is the subshell. Okay? Now, for you to understand what they usually do, instead of putting a number, they designate letter. So what does it mean? So let's say you have here N1, 2, and then L is 0, 0 and 1. So if you're going to designate, this will become 1s, this will become 2s, and this become 2p, because they designate the letter here for N. Okay, for L that has a value of 0, you have S. For L that has a value of 1, you have P. Now, when do you have an L with the value of equals to 2? When N is equals to 3, right? Because if you have 3, what are the possible value of your L? You have 0, 1, and 2. Okay, so if you're going to put them, this is what? A 3s, a 3p, a 3d. Okay, so this is now your subshell. This is now another subshell. And this is now another subshell. But if you're going to put them together, what do you call them? Okay, the letters represent the numbers here. I did not designate it, it's in the book. But the way that I want my student to do is usually, oh, it's not yet here, but I'm going to put here. So if you're going to look at the letters, letters there, usually if you have an S, this is the one that is represented. If you have a P, this is the one that is represented. If you have a D, this is the one that is represented. So the way I ask my student, so this is what? Spear, this is peanut, this is double peanut for D, and this is the F that we have there, which I call the flower. Okay, so it's in the shape. Okay, so the second quantum number that represents the shape of the orbital. So if it's an S, the shape is like this. So this is how the 1s orbital looks like. This is how the 2s orbitals looks like. So as you could see, the bigger the n, or the higher the value of the n, the bigger is the orbital. Now, if you have a p, that is when L is equals to 1, you have it like this one. It's like a peanut here. And if it's a D, except for this one here, you have like a double peanut. Okay, so it has something to do with the shape. So what does it mean? Depending on the value of the L, the value of the N, you have a corresponding value of your L. Okay? Because what happened here, this is really a 2, 1, and this is a 3, 1, and a 3, 2. But instead of using this number, you designate the 0 as letter S, 1 as P, 2 as D, 3 as F, and if you go on, you follow the alphabet. Okay? But usually we only do until the F. Okay? So we already have 2 quantum numbers. Okay? But it says there it's the 3 quantum numbers that describe an orbital. So we now go with the third one. Okay, the magnetic quantum number. So we have N as the size, L as the shape, the M sub L now, that is your spatial orientation. So it's a quantum number that distinguishes the orbital of an N and an L that is of a given energy and shape but having different orientation. So the magnetic quantum number that we have here depends on the value of L. So what does it mean? If L depends on N, M sub L also depends on the value of L. And the way that you have here is it can have an integer value from negative L to positive L, including 0. So what does it mean if we're going to put the 3 quantum number like this? So if I have 1 here, I have 0 here. What's the value of M sub L?
Three.
Anyone?
1.
Huh?
-1.
What's the value of M sub L if I have the given N and L there?
3.
1.
0. Remember, the value of M sub L is from positive L to, no, negative L to positive L, including 0. Now, what's the value of your L?
0.
That's it. You don't have other value. Now, what if you put it like this? What's the value of M sub L that I have here?
1.
0.
Okay?
0.
Now, what if I do it like this?
1.
So I have how many value here?
2.
I have a negative 1, a 0, and a positive. Because that's what it says there. The magnetic quantum number, which is your M sub L, depends on the value of L and can have any integer value from negative L to positive L. Okay. So let's try to work on here. So when you have N is equals to 1, the only value of your L is 0. So if you only have a value of 0, that means your M sub L is also equals to 0. Make sense?
Yeah.
Okay.
Yeah.
So what does it mean? Your 1s is 1 orbital. So if you're going to look at the quantum number of that, it will be 1, 0, 0. So 1, 0, 0 describes the 1s orbital. So if you have a 2s orbital, what's the quantum number that you have there? You have 2, 0, and 0. Remember, the 2s is described by the first 2 quantum numbers. You designate the letter S for an L equals to 0. Okay? So that means you also have one orbital. Now, what if it's a 2p? So what are the values of N and L for 2p? You have 2 and 1. But what's the problem with M sub L? You have -1, 0, and +1. So what does it mean? You have 3 sets of quantum number. You have what? A 2, 1, -1, a 2, 1, 0, a 2, 1, +1. And each of them describes an orbital. So if I ask you the question, how many orbitals does 2p has? What is your answer?
3.
The answer is 3. And each of these is designated by these quantum numbers. So we could say the s orbitals has 1, the p orbitals, they have 3. Okay? If I'm not mistaken. So here, for a given subshells, there will be 2L plus 1 values and therefore 2L plus 1 orbitals. So what does it mean? If L is equals to 0, how many orbitals do you have? So 2L plus 1. So you change this to 0. It will give you what?
1.
1. Right? And if you have L is equals to 1, so 2 times 1 plus 1, do you have 3
3.
orbitals? So let's go. There's still other thing there. So when N is equals to 2, your L has 2 values, 0 and 1. You know this is the S and this is a P. So when L is equals to 0, your M sub L only has 1 value. So there is only a 2S subshell with 1 orbital. Now when L is equals to 1, your M sub L has 3 values, -1, 0, and 1. So there is a 2p subshell with 3 orbitals. Okay? So shell, subshell. So shell is defined by N. Subshell is defined by L. Okay? So when L is equals to 1, how many orbitals do you have?
Three.
Okay, those are the questions that's going to be asked in your exam. So when L is equals to 0, how many orbitals do you have?
1.
1. Okay. So let's go to the next one. We go until I think until 4. So when N is equals to 3, you have 3 values of L. It could be a 0, 1, and 2. So that means we designate it as 3S, 3P, 3D. Okay? So when M sub L is equals to 0, again, your M sub L has only 1 value, which is 0. So there's only what? 1 orbital for the 3S subshell. Okay? Now, when L is equals to 1, the M sub L has only 3 values, -1, 0, and 1. So there is a 3p subshell with 3 orbitals. Now, when L is equals to 2, M sub L has only 5 values. That's -2, -1, 0, 1, and 2. So there is a 3d subshell with 5 orbitals. But how are we going to predict that it is 5? Aside from this, aside from counting 1, 2, 3, 4, 5. You use this thing, the 2L plus 1. That will give you the number of the orbitals. Are we clear on that?
Yes.
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 Because the one that you'll be going to ask is, what's the number of your orbitals given either the n or the L? So you were asked how many orbitals when n is equals to 3. How are we going to look at this? So we have to look at the subshell. So I have a 3s, a 3p, and a d. So an s, p, and d, or a 0, 1, and a 2, right? So you know a 0 has 1 orbitals, a 1 has a 3 orbitals, a 2 has a 5 orbitals. So when you add all of them, you have 9 orbitals. So there's a shortcut there. Okay? Before we go to that shortcut, what if I put this n is equals to 2? So if n is equals to 2, I have what? 1 and 3. That is equals to 4 orbitals. This is 9 orbitals. So how many orbitals now when n is equals to 1? So I only have 1. So what is the shortcut that I have? How can I get the number of orbitals when n is given? Can we say it's just n squared?
Yes.
Does it make sense? That if you are asked for the number of orbitals for a given n, all you need to do is square the n. If you are asked how many orbitals when the L is given, then you're going to use this thing. Or you can do it the hard way. Okay? So here, I put here the n is equals to 4 and 5. So in the F subshell, there are 7 orbitals. In a G subshells, which is very rare, I think it doesn't include in our Gen Chem, there are 9 orbitals. So if you're going to look at that stuff that we're talking about, this is what we have. So as you're going to look at here, if we're going to look at the orbitals, we're going to designate them. That's 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. So how many orbitals when n is equals to 4? Anyone?
16.
16.
It is equals to
16.
16. You do the shortcut. How do we get 16? The squared of 4. What is the hard way? You count this one. 1 plus 3 plus 5 plus 17. Plus 7. So all of them will give you 16. Analyze. So if the one that is being asked, given the n, so it's just the number of orbitals is equals to n squared. Now, what if the one that's being asked is how many orbitals are there in 3p? What is your answer?
3.
Okay. The answer there is 3. You get it from the p. What is p in terms of L? What is the designation for p? What number?
1.
L. So that's 1. So to get the 3 there, you use this. Okay? So, what is the set of the quantum number that we have here? So, it's just the N, the L, and the M sub L. And each orbital, they have 3 sets of quantum number. So for the 2p orbital, that means you have 3 orbital. The 2, 1, negative 1, 2, 1, 0, 2, 1, positive 1. The same thing with the 3p. 3, 1, negative 1, 3, 1, 0, 3, 1, positive 1. Okay? So each of these pertains to an orbital. So if we're going to look at the energy level of this orbital, this is what we have. So as you could see there, each number is higher. I mean, depending on the number you have here, a higher energy level. So the 1s, and then you have the 2s, the 2p, and then the 3s, the 3p, the 3d, the 4s, the 4p, 4d, and the 4f. So the figure shows the relative energy for the hydrogen atom shells and subshells. Excuse me. Now, if we're going to what we call summarize what we have so far, so as I told you, if it's the n quantum number, it has something to do with the size. Or if we're going to look at it in terms of the house, it's the size of the house. The higher the value of n, the bigger is the size of the orbital. In terms of the house, the higher the n, the bigger is the house. L has something to do with the shape. Okay? So this is what? This could be your S, this could be your P, this could be your D, and this could be your F. So each of the L value, okay, instead of using the number, we designate it with a letter, they correspond to a particular shape. The way I told you, S for sphere, P for peanut, D for double peanut, and F for flower. Because that's how the shape looks like. Now, the M sub L, on the other hand, has something to do with the orientation of the house. Okay? In the S, there's only one orientation, right? That's why you only have one orbital. But if you have in the P, there are 3 orientation. How do we know that orientation in terms of M sub L value? There's a negative 1, there's a 0, and a positive 1 value. So each of that value has their respective orientation. That's what it means. Okay? Now, the fourth one that we have, as I told you, the first 3 is the only one that you need to identify the orbital. The fourth one has something to do with just the spin. And it only has 2 values, either a positive 1/2 or a negative 1/2. So the way that they look at this is the spin. So the way that you look at the spin, what do you call this? Clockwise. And the other one is counterclockwise. Okay? And the value that you have for this is just either positive 1/2 or negative 1/2. So if you combine the 4 quantum number, the last quantum number should either be positive 1/2 or negative 1/2. Okay? So let's try, because these are the type of questions that we'll also ask in the exam. So which of the following are permissible sets of quantum numbers? So which of them are allowed? So how are we going to solve this question like this?
Eliminating.
So let's try to solve them. So you need to remember the information that you have about the quantum numbers. Okay? So n is equals to 4. Is this allowed?
No.
Okay. So when n is equals to 4, the value of L can either be what? 0 to
3.
3. So that means it's not allowed. Okay. Is that clear?
Yes.
The others?
Yes.
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 So you have to go back to the definition. So why is it not allowed? Because the value of L depends on the value of N. Okay? How about the second one? Is this allowed?
No.
No.
I think it is.
But the L equals 2, not 1.
But isn't it,
N minus 1.
this is from 0 to 2?
Yes.
So any value from 0 to 2?
But the ML doesn't.
And the ML, since this is 2, so the M sub L value would be from -2 to
Positive 2.
2. So that's how you're going to look at it. Or the way that you look at it, if you remember the table here, that one. So where is that? 3 and 2. So the value of M sub L can either any of these 5. Analyze, convince yourself it's allowed. Not because I told you.
Okay.
So the value of the next set of quantum number depends on the previous set or previous number of previous quantum number. Okay, that's why here n is equals to 4, L is equals to 4. That's not allowed because the value of your L is just 0 to 3. So you cannot continue anymore because you're already done here. So the same thing here. 3. So the possible value of L is from 0 to 2. Now the value of M sub L depends on what value of L you have. So if it's 2 here, so that means it's any 5 numbers between -2 to +2, including 0. And M sub S is either positive or -1/2. So how about the third one?
No, because MS is 3.
Okay. So the first 3 quantum numbers are okay, but this one
Spin is too much.
is not okay. Okay. Now the last one, it's also allowed. Okay. So if you're going to look at the summary here, but I want you to know why is it permitted and why is it not permitted. Okay. So let's go to the orbital shape. So we already discussed what the L value that we have here. So as I told you, when you have an S, it's a spherical. When you have a P, I always call it the P naught, just as a given way. So what do you mean the last one? You cannot have a 4 because the L is just a 3. The value here depends on what's given here. So if you have a 4 there, then you can have the positive 4, -4 to +4. Okay. So when you have a p orbital, if we go back, there's 2 lobes along with a straight line through the nucleus with 1 lobe on either side. So it's not the one that has like this. That's why I call you a peanut. It's really a peanut shape like that. Or what's the next dumbbell maybe? And the orbital has a more complicated shape. It's more of a clover. Okay, so this is how the s orbital looks like. So if you're going to look at the s orbital, this is the cross sectional, and then if you cut them, this is how it look like a Pac-Man. If you're going to cut it through, okay. And the p orbitals. So remember, you have a -1, a 0, and a +1. So those are the one that represent it. Okay, so you can have either a 2px orbital when it lies on the x orbital, a 2py when it lies at the y orbital, or a 2pc if it lies on the c orbital. Okay, and if you have what we call the d, so this is what the -2, -1, 0, +1, +2. So those are the designation. Those are what we call the orientation that they have, depending on the given m sub l value. Okay? So you can have it like this. You don't need to memorize this thing. The possible question that you're going to ask is, you should know what an s orbital, p orbital, or d orbital looks like. But it will not ask you what the designation of each orbital that you have. Okay, so the way that it look at it is where they lie. So dxc, so they are in the x and the c orbital. dyc, they are in the y and the c orbital, and dxy, they are lying in the x and the y orbital. So the dx squared minus y squared, that means they are in between those things. And the odd thing here, like a ring, that is the dc squared. So the F is not really what we call discuss, but just to show you how it looks like. So we have here, what is the designation here? -4 to +4, right? So they looks like a flower. The way that I designate it to simplify the wordings. Okay, so these are the different shape of the orbitals. So the thing that you're going to be asked for questions like this, okay? You have to determine how many orbitals when n is given or when l is given. And then how many electrons that you have. So how do we designate, or how do we determine the number of electrons? We just multiply by 2 the number of the orbitals. Okay? Analyze. Ask yourself, if you're given a set of quantum numbers, can you determine what orbital it is? Yep. You always multiply by 2 the number of orbitals that you have.
Can you find an element?
Question.
So would you ask us if we want to find an
No,
element?
I already asked you some of the possible questions that would come out.
Thank you.
You might be asked if the set of quantum numbers is possible. You may be asked what is the orbital if you're given the set of quantum numbers. So those are the possible questions that will be given to you. Okay, those are the questions that you will be asked. Okay, so let's say if you're given, I'm trying to use, so if you're going to write like this, no. So what is your answer there? Write the orbital when n is equals to 4, L is equals to 2, and M sub L is equals to 0. And then there's a follow-up question there. How many orbitals are there? Or we could say, how many electrons are there? So what's the answer that you have here? No, you have to answer first the question there. Write the orbital when n is equals to 4 and L is equals to 2. So what's the orbital that you have there? You don't go to 16 again. The question is write the orbital. You are not asked the question how many orbitals. Okay? So maybe you have to ask yourself, are you being asked how many orbitals are there?
No.
So how are you going to write the orbitals for this one?
With the number and letter.
So 4 and
P.
is it P? I don't think it's a P.
F. D.
Please don't guess.
I didn't guess.
You always have the S, P, D, F. 0, 1, 2, 3. Right?
P was 2.
So that's the answer there. So how many electrons are there? If you are not given this one, what will be your answer? If this is missing, you're just given like this one. What is your answer?
10 electrons?
So how many electrons are there when n is equals to 4 and L is equals to 2? How many electrons?
10.
So you have there an orbital that is what we call a d orbital. Right? So a d orbital has how many what? M sub L? 5. So the answer there would be 10. You get that? So this is here, huh? But if you include this one, what is your answer? Because you're given the exact orbital. Okay? So let's try again. Okay, so I have it here. So for n equals to 3 and L is equals to 2, how many orbitals and electrons are there? Write the orbital designation. Okay. So this is equals to, what's the orbital designation here? 3 and D. Okay. So how many orbitals are there?
5.
5. So whenever you have an orbitals, the first thing that you're going to do is the L value given. If the L value given, you're going to base the number there on that given L value. No, you squared it if n is the only one given. That's why I'm trying to explain it to you now. When L is given, that's it. You're going to use the 2L plus 1. But if that is not given, if n is the only given, then you're going to square it. Is that clear?
Yes.
So where do I get the 3D? Because this is the one that is given. So I have to find the designation for that orbital. So how do we name the orbital? The n and the L value. That's why I'm still taking time in doing this thing, although we're done with the chapter, because I know this is not easy. Okay, so let's try another one. So if this is a 5 orbitals, that means you have there 10 electrons, because electrons is always times 2 of the number of the orbital. One orbital has 2 electrons. Okay. So how many orbitals are there if you have n equals to 2 and L equals to 0?
1.
2s.
1.
You only have 1. And if you are asked what's the designation,
2s.
it's 2s. Okay. Now how about this? How many orbitals and electrons are there in n equals to 3?
9 orbitals.
So that's the one that you're going to square it. And the electron will always be times 2 of the orbital. So you have there 18 electrons. Okay. Now, is this number possible? Yes or no?
Yes.
Is this set of quantum number possible? Yes or no?
No.
Oh, no.
The answer is no. Because when this is 1, the only value of this is
It has to be 0, don't it?
0.
Yeah, 0.
So this is not possible. Now, how about this? Is this possible?
Yes.
Yes.
Yes, it is possible. Now, how about this? Is this possible?
Yes.
Is this possible?
Yes.
Yes.
No. Why? This one. Where does this depend?
L.
Can you have 1 when L is 0?
No.
No.
Oh.
Okay, what did I told you? The number depends on the previous given quantum number. Okay, how about this? Is this possible?
Yes.
Yes.
Yes. This one. Is this possible?
No.
No. Okay. So at least you're already given some example here. And the quiz that we have by 1:30 is all about this one. It's all multiple choice, 5 items in 5 minutes. You have to done by 1:50 because we're going to start now with chapter 8, which is a little bit related to the present chapter that we have. The chapter 8 will answer you the question, why 2 electrons? Okay, because it's not really clear why 2 electrons that we have, because chapter 7 and chapter 8, they have to be presented at the same time. So if you have the chapter 8, if you're going to look at here, it's the first discussion that we have there is really a continuation of chapter 7. Okay, so if we're going to look at here, electron configurations and periodicity. So the information that we get from chapter 7 is just very, we could say, linked to, or it's really very informative and linked directly to chapter 8. So remember the spin quantum number that we have. How did they know that it is a positive 1/2 and a negative 1/2? Okay. They knew it because they study on it. In 1921, Otto Stern and Walter Gerlach, they first observed the electron spin magnetism. And in the given diagram below, okay, what they did is a beam of the hydrogen atoms divides in two while passing through a magnetic field. And they correlate this value as a positive 1/2 and a negative 1/2. So what does it mean? The atom would spin like this and like this one. Okay, so the way that they're going to look at this spin orientation that they have, so it can either be, in this case, clockwise, counterclockwise, in this case, clockwise. So there are only 2 possible spin orientations of an electron, and the conventions for the M sub s is given here. So I told you this is really related to the chapter 7. So I don't want to stop. Still have time to at least show you that for each M sub s, there's 2 possible values that you have there. So what does it mean? There are 2 electrons that you have there. Okay, and the 2 electrons that will occupy that thing is of opposite spin. So what happened now? So we already have the designation, the 1s, the 2s, the 2p. So what we can do, we can use that concept in arranging how electron is going to fill up in a given atom. And the way that we call them is electron configuration. Okay, so if you're going to look at the electron configuration of an atom, this is just the distribution of electrons among available subshells. What's the subshells that we have? The S subshells, the P, and the D. Okay, so what are we going to do now? The orbital designation that we have, we call it the orbital diagram. Okay, so the orbital diagram here of an atom shows how orbitals of a subshell are occupied by the electrons. And orbitals can be represented by circle, okay, with electrons represented as either what? Arrow up or arrow down. So I'm not sure if the first time for you to have it like this and you designate this as 1s and you put an arrow there. And usually you assign that to a hydrogen. Okay, If you put another arrow there, then that is a helium. Okay? But what's the difference of the hydrogen and the helium? So on hydrogen who have like this, a helium would have like this one. See the difference? What tells you the difference between the two?
You choose that number?
That number that you have there. Okay? So what we're trying to do here now is how are we going to write this electron configuration? Okay? But before we do that, we have to discuss this so-called Pauli exclusion principle. So this is from Wolfgang Pauli, a German. So what does it says here? Okay, the Pauli exclusion principle summarizes that experimental observations that no two electrons in one atom can have the same quantum number. So what does this mean? Okay. What does this quantum number mean? So for instance, the one that I told you, the 1s1 and the 1s2. How can we designate that thing? So both of them are what? 1, 0, 0. The other one could be what? Positive 1/2. And the other one could be 1, 0, 0, negative 1/2. If you summarize the Pauli exclusion principle, it just means that within one orbital, electron must have opposite spin. It also means that one orbital can have at most 2 electrons. So this is the explanation why I asked you, if you're asked for the number of electrons, you multiply the orbitals that you have with 2. Because an orbital can only have at most 2 electrons. And how do you differentiate the 2 electrons in a quantum number? This one. Analyze. Both of them are what? What's the orbital designation for this given set of quantum numbers? Anyone? Both of them are 1s, right? That's not 2s. That's not 2s. You see 1, 0, 0, 1, 0, 0. That's 1s. But how are you going to differentiate the electrons in that? Because they would occupy 2 electrons. So one would have a positive 1/2, the other one would have a negative 1/2. So that's the Pauli exclusion principle. So Pauli exclusion principle just states that no 2 electrons in an atom can have all 4 quantum numbers the same. Okay, an orbital can only take at most 2 electrons. So what does it mean? For an S subshell, you can only have 2. For a P subshell, which has 3 orbitals, you can have at most 6. For a D subshells, which has 5 orbitals, you can have at most 10. And for an F subshell, which has 7 orbitals, you can have at most 14. Is that clear?
Yes.
Everybody?
Yes.
Yes.
Okay. So now we have this so-called ground state and excited state. So what does this mean? So remember, we have the designation maybe like this. or you can make it square. So ground state. So ground state is the lowest energy configuration of an atom. So that's a stable configuration. So let's say if you have hydrogen. So this is the ground state. Your electron is here. Now, how are you going to make it into an excited state? That electron will not be in 1s. It could be here. Or we could say like this one. But since you only have one electron, you know it is hydrogen. Or the way that they designate it, maybe 1s and then you have 2s. And then the 2p and then the 3s. So you have here 1s, 2s, 2p, 3s. So whenever you have an excited state, that means your electron is not at the lowest state, lowest energy configuration. So if you have a hydrogen, you could put it like this. But it can also be like this one. So what's the difference between the two? So this is the ground state. This is the excited state. So in the excited state, you excite the electron to a more or a higher energy level. So that's what it means between the ground state and the excited state. And we know in an excited state, it's not a stable state, right? Do you agree with me on that?
Yeah.
Okay. Yeah. Can you be excited all the time?
No.
Yeah, I'm so excited. Okay. There will come a time that you're going to fall down because that is the ground state. That is the more stable state. Okay. But there's a chances that when energy is absorbed by the system, the electron can go to a much higher energy level. So you have the unexcited state. So that's the concept of the Bohr. So they still go, what we call maintain the concept of the Bohr model, okay, in the quantum mechanical model of the atom. Now, another thing that you need to remember is the so-called building up principle. The German word for that is Aufbau principle. So this is the scheme used to reproduce the ground state electron configuration by successively filling subshells with electrons in a specific order or building up. So what does it mean? When you fill up the electrons on the orbital, you fill it up according to the energy level. Okay? So energy are added to the available orbital with the lowest energy. So this order generally corresponds to filling the orbitals from the lowest to the highest energy. Now note that this energy are the total energy of the atom rather than the energy of the subshells alone. So the question that you ask, what's the sequence? Okay. So either you do this thing or you follow the so-called N+L rule. What is the N+L rule? You just add the quantum number with the azimuthal quantum number. So 1s is equals to what? 1 plus 0 equals 1. 2 plus 0 equals 2. Okay? So the way that you're going to build it up is depending on the N+L rule. Okay? Or the way that I ask my student is you round it, you write all the S in one column and then the P in another column and then the D in another column and each of the principal quantum number on the same row. Okay? And what you do, you draw the arrow diagonally. Okay? Now, let's try to follow the N+L rule and see if the sequence is the same. Okay? So as you could see here, okay, between 2s and 2p, so what do you have here? 2p is 2 plus 1, that is equals to 3. So does it make sense that you filled up the 1s first and then you go to the 2p? Right? Now, where's this anomaly comes? This one. So as you can see, why is 4s filled up before the 3d? The n plus rule has an explanation on that. Okay, so 4 plus s is equals to what? 4. 3 plus 2 is equals to 5. So here it says, before you fill up the 3d, you have to fill up first the 4s. Does it make sense?
Yes.
And then you might say, how about the 4p? What is the 4p? 4 plus 1, right? So they're equals to 5. So what's the rule if they're the same? The one that is the lower principal quantum number will be filled up first, followed by the next higher principal quantum number. Okay, so this is the sequence that you have. Now you may ask yourself, is there an easier way for us to do this instead of memorizing this thing? Because if you're going to line up the sequence that you have from here, this is what you have. So as you could see here, the 4s comes before the 3d. But is there an easy way? The answer is yes. No, not doing the Christmas tree that we have here, but looking at the periodic table. So this is the easiest way that you have. These are all the 1s. Or all, not the 1s, but all the s orbital. And these are all the p orbital. And these are the d orbital, and this is the f orbital. Now, how do we know the 1s? The first row that you have here. Now, in the first row, it's all s. You include the one that you have here on this side. Okay? The second, you now have the s and the p. The third, as you can see, you have here the 3 and the p. And then you may ask, where is the 3d? This is the 3d. But the problem with the 3d, it is in the fourth period. So what usually happens if it's a d? So whatever the period, minus 1. Right? So 4 minus 1 will give you what? 3.
3.
And then you go said, how about the f? Why did it start at 4? So what do you think the rule for the f? Whatever's the period minus
2.
2. It is in the 6. So minus 2, that will give you the 4f. So I'm leaving it up to you if you want to memorize the thing or you want to do it this way. Because if you're going to look at this in the 1s, s can only have at most what? 2. So this is the S1 and this is the S2. Okay? And then in the P, this is the NP1, NP2, NP3, NP4, NP5. That one should go to the ester. And then this is the NP6. What is the end there? Depending if it's what? Second, third, fourth, or fifth period. The same thing with the D here. So you have D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. Okay? So those are how you do the electron configuration. So next meeting, we're going to have an example of this configuration. How are we going to write the electron configuration in a given element. So I'll take this as a question and answer portion right now. So do you have any question?
No.
While I'll open the quiz that you have. So it's just a 5 minutes, 5 multiple choice question. My daughter is fine. She's negative, but she's here with me. So question.
Professor, how long is the quiz?
5 minutes.
Okay.
And you have until 1:50 to finish it. So question. Some of you might be taking it now. So my advice to you, if you want to drop the course, don't do it because there's no Gen Chem 1 next semester. So the earliest that you can take it if you want to drop the course is on summer. The course is not going to be available by next semester. That's what the department told me. Okay. And I was a little bit disappointed when Dr. Lictina emailed me the grades of your lab so far. Some of you has not submitted any lab reports. So you are in danger of failing the course even if you are passing in the lecture. So I don't know why you didn't submit any lab report because I think there's already 3 lab reports so far, and what I get there is 30 entries that you have. No, I didn't get from CK. It's just Dr. Lictina that I got.
We're on the 5th lab report right now.
No, I mean the one that he sent me is
oh, the graded ones.
Yes, 3 entries.
Okay.
So these are just for those who are concerned, because some of you are doing well in the lecture.
So, the OWL homeworks, are you going to be uploading those grades to Blackboard or?
No, I'm not going because it's available in the OWL. It goes straight to my record. Because sometimes when I do it manually, I am prone to error. Okay. I cannot do anything with the OWL. That's what all Gen Chem students are doing. I even reduce it. Usually before there's 5 questions in each item that's being asked, I reduce it to 3. And then before, you are only allowed 3 attempts, but now we make it 10 attempts. The quiz is from what we did today. It's open notes, so that's the thing. It's just time pressure. So question?
Professor?
Yep.
I can access the quiz on Blackboard because of a void. Is there any?
You have to make sure you come back as soon as possible.
Okay.
Because I cannot let you in. I don't have the way or authority.
I know, but I was just asking if like I could maybe email the answers or. any other?
No, you just have to do it during the what you have there in the system.
Okay, thank you.
Yep. Okay. So if you have no more question, I'm giving you the last 5 minutes to answer the quiz. And please don't use that in your other class. Okay? Because if I get an email from another teacher, I will ask the name and I'm going to make the quiz 0. Because you have enough 5 minutes to do it. Later on. I'm not done yet. Okay? So see you. Stay safe. See you on Thursday.
Thank you.
Thank you. Bye.
So this is the only quiz. You don't have any quiz in between. Okay?
Thank you.